And all right. And I guess I should start that explanation again. I am Zach, or Reshner Fox, whichever you prefer. And this will be an entry-level electronics theory and construction class. We might get into some construction eventually. I'll put the camera on the workbench. I apologize ahead of time. I have a really bad quality webcam to do this with, but hopefully it'll work out, and hopefully my tablet won't stop working on me. So anyways, this will be an entry-level class, pretty basic stuff. We'll see how far everyone wants to go, but it'll be essentially anything you need to know regarding the questions on the entry-level amateur radio licenses for either US or Canada. If you have any questions, you can direct it on the left bar in Hangouts. There's a Q&A app. Just click that, put your question there, and I'll check it every so often. All right, so we'll go ahead and get started here. So let me delete that and make sure I can draw. So first off, talk about electricity. We're all using electricity right now, hopefully. We're going to talk about the flow of electrons. So, I don't like this color. We'll go there. So, what is electricity? It is flow of electrons through a conductor. All right. So let's draw us a little diagram here. Boop, boop. And we'll make this a light bulb. All right, so if you take a battery has two terminals, and the two terminals provide an electrical potential. So first of all, we're going to talk about current. And electromotive force, or potential, which we call voltage. And how that all ties into power. So, flow of electrons in a circuit is called a current. All right, current which only flows in one direction, such as what you get from a battery, anything battery powered, is called direct current, or DC. All right. So pretty simple here. You have a battery here. There are electrons flowing in one direction or the other. So in the old times of the very beginning of electronic exploration, a guy named Volta took two dissimilar metals, something like zinc and copper, and stuck them in an electrolyte, which is a weak acid, and it created an electrical potential between the two, which he could electrocute frogs' legs with, and we refer to that as being galvanic. And there's a whole other history into that we won't go into. And Volta understood that it was the flow of electrons in a conductor flowing in some direction, but we didn't know which way the electrons were flowing. And so they made a guess, and they guessed that, okay, we'll just call this side the positive side. We'll guess that the electrons are flowing this way. And they had a 50-50 chance, and they got it wrong. So we refer to usually in a circuit diagram, we can think of it as flowing in either direction. It'll work with the equations, but sometimes it is important to know that this is the way electrons are flowing. But for the sake of our diagram, we'll do it both ways. And so we have our current flowing positive to negative this way and all the way back to the battery here. And we'll call that our current. But our electrons are actually going this way. And that's important to know in a few circumstances. So we have direct current. It's pretty simple. Electrons flowing in only one direction, and they flow through a conductor, which is any sort of material which permits the flow of electrons or an electric current. All conductors have a property called resistance. And just like it might sound, it's a property which resists the flow of electric current. All right, and there's a relation. A guy named Georg Ohm noticed that there was a correlation between voltage, which is electromotive force. We'll get into that in a little bit. And there was a correlation between voltage and current. And it was directly proportional, and we call this proportion, he called this proportion resistance. So he made a few empirical guesses and found that voltage is directly proportional to a property called resistance, which is the inverse of conductance, but we don't really have to worry about that. And let's see. We measure resistance in ohms, named after Georg Ohm. And so in any given circuit here, our conductors here have a negligible resistance, so we're just going to ignore it right here. But our halogen lamp, let's say this is an incandescent bulb or a halogen lamp, it'll have a specific resistance. All right, and it's that resistance which gets dissipated as heat and light to produce light from our light bulb here. And so let's say this is a 1.5 volt cell. All right, this is your standard AA battery, basically, and we have a lamp of some unknown resistance. And oops, let's say we measure our current here. We'll put an ammeter in here. All right. We can, using this equation here, magic, know, based on our voltage here and how much current is flowing, we can find out the resistance of this lamp, and we can find out how much power it's using. But first, let's talk about a current more. And let's see, will you move? Yes, you will. Oh joy, you've messed up everything. All right, we'll talk about current. So current, the technical definition is how many coulombs per second are flowing through our circuit. Actually, we're not going to use A, we're going to use I. Coulomb per second. What is a coulomb? A coulomb is an arbitrary number of electrons. So if you were to go down on a subatomic level here in our wire, and you were to count the number of electrons going through that wire, that would equate to a measure of coulombs. And so we generally want to know how many coulombs are flowing in a given time period. So we use amperage, which is measured in amperes Okay. And Ohm knows that that current and voltage, which is something else. If you think of some people don't like this, but there's an analogy we can use. If you think of the flow of water as, or the flow of electricity as water, if you have a big wide path for water to flow in, oops, come back, and we change our colors here. If you have big wide tube for water to flow through, the pressure is relatively low, even though there's a large quantity of it. And so we can think of pressure as voltage. It's the electromotive force. It's the force that's moving the water. But if you have more water, that equates to more force. And if you restrict that flow, like this, well, the same amount of water has to pass through this small space, this tight, it meets this resistance, and so the voltage increases. Voltage is greater here, current is the same, voltage is greater. All right. So let's go back to our Ohm's law here. This is what this is. Ohm's law. And we know that the current through a conductor is directly proportional to the potential difference between 2 points, or voltage. And this is true most of the time. So for sake of theory, we'll just pretend that Ohm's law is true everywhere. Unfortunately, it's not. And for the devices that it doesn't work in, we call those non-ohmic devices. And devices which do follow Ohm's law, like wires and resistors, are ohmic. So let's get into the components actually. What is a resistor? Usually it's made out of carbon. We use this schematic symbol for a resistor. Sometimes it's also just drawn as an open box. Resistor could be anything. Any sort of conductor, if it's not a superconductor, will have an inherent resistance to it. The thinner the wire is, the higher the resistance. So in the case of resistance, you can calculate based on cross-sectional area of a wire. So if you chopped a wire and you measured the radius or the diameter, and you used pi, so it's what area is pi r squared, or you could work it out with diameter too. Either way, cross-sectional area is proportional to resistance. So the more cross-sectional area you have, the less the resistance. And that's important in a lot of things. You think about overhead transmission lines, power coming from a power plant over here. See, we got factory, smokestacks, blah, blah, blah. All that way it has to come, that's voltage losses before it gets to your house. So the better the conductor, the less the losses. And I'm not going to draw pylons. Wasting too much time. Anyways, moving on. Let's check in here. Let's look at some schematic devices. Look at some schematics. So we saw a resistor here. A lot of resistors. I could probably show you some. They're usually made of carbon, because carbon isn't a great conductor, and the more carbon you have between 2 points, the more resistance we have. And we represent it with every schematic symbol we'll be using will have a letter designation. So resistors, it's R. Capacitors are important. Capacitors store a charge. They're kind of like a battery. You can charge and discharge very quickly. So we have resistors, which we measure in ohms, which we represent with a capital omega. And capacitance, we represent in farads. And we'll talk about that in a bit. Battery, we can represent a battery with 2 uneven lines, like so. This generally represents a single battery cell, and we can stack our cells together. And so we got positive on this side, negative on this side. Diode. Diodes are important. Diodes are sort of like one-way valves. They only allow electricity to flow from change. Damn it. Why aren't you changing? Here we go. So we got anode and cathode. Diodes only allow electrons to flow from cathode to anode. They can only go this way. Can't go this way. And that's pretty important. It serves a purpose called rectification, which you'll understand eventually. And important to everyday electronic life is a device called a transistor, which we'll get into probably another day. And let's see, switches are pretty easy. It's just a break like that. You can represent it like that. We can also have variable components. We can have a variable resistor called a rheostat by putting an arrow through it, kind of like that, or with an arrowhead on the end. Same thing with a capacitor. We can have a variable capacitor like that. There's another type of variable resistor, which is very common, called a potentiometer, which has 3 terminals right there. And we'll talk about that in a bit with voltage dividers. And actually, let's go ahead and start with that. We'll start with a voltage divider. So I'm going to wipe out everything here. And we're going to, oops, unwipe everything. Wipe out everything. And make sure I'm at the top. All right. So we know that electric flow is flow of electrons, and we can have a resistance, usually we call a load. So we'll call this our load. Let's go back to Ohm's law. B equals I R. All right, so we can measure voltage across our load. Let's say we use a device called a voltmeter, and we'll measure it between here and here. All right, so we'll draw this out and we'll put in our voltmeter. All right. We can also measure current. So remember, counting electrons. We'll put our ammeter here. And let's say this is an unknown resistance. Not sure what that is. All right. But we've measured a voltage of 100 volts here. And let's say 100 milliamps here. Pretty easy. Just plug it into our equation here. We have 100 volts equals 100 milliamps, which is 0.1 ampere, times our resistance, not sure what that is, divide by 0.1 amps on both sides. And our resistance is magically 1,000 ohms, or 1 kilo ohm. And that was an awful omega. Anyways, now we know our resistance here. There's another important equation relating power and voltage and current. It's pretty simple. Oops, that's not a P. Power is current times resistance. I'm sorry, current times voltage. I'm not thinking right. We can plug in Ohm's law and rework this and find out power is also current squared. That was awful. Current squared times resistance. If we given Ohm's law, also voltage squared over resistance, I believe. Let me check my notes. Yes. All right. So we know these electrons are doing work. So even though the same number of electrons that leaves the positive terminal or the negative terminal of the battery that travels, let's get a different color, travels all the way through our circuit, the same number of electrons that leaves the battery here ends up at this terminal too. But remember that voltage is the potential to do work. It's an electric potential. So we've lost our energy here, and we know from physics, because of conservation of energy, that it has to have gone somewhere. It didn't magically disappear. And all of it in this circuit got converted to heat. So this resistor would just heat up. It doesn't really do anything. So let's find out how much heat we're wasting. Pretty simple. We plug it into our other equation here, now that we have the resistance. Or we already have voltage and current, so we know that power is 100 volts times 0.1 amp. Simple multiplication, we get 10 watts. This might be a unit you're familiar with. 60-watt light bulbs, 10-watt light bulbs. So all that 100 volts and 0.1 milliamps that went into that load got converted to heat. Luckily, not everything is so useless, but I mean, you think about it, computers are basically space heaters, because even though they're performing a task, even though they're crunching numbers, all the power that goes into your computer inevitably ends up as heat. So kind of cool. Let's look at a different schematic. Let's put in our diode. Diodes are important. I'm going to draw it a bit differently. Instead of using battery, I'm just going to say, let's use red. I'm just going to say that we have a positive voltage source and we have a load. There we go. This is an important diagram here. It means ground. We'll just use it as it's the negative terminal of a battery. If my keyboard works here, we have a positive voltage source here. So we have a potential here through a load. We can also wire in another load in parallel. As opposed to, let's draw another one over here, is we have our other circuit with positive voltage supply, and we've got two resistances in parallel. I'm sorry, in series. So series, parallel. All right, and it's pretty simple mathematics. If you have two resistances here in series, then the total resistance of the circuit, let's change colors, is just the sum of the resistances in parallel or in series. I cannot talk today. Rn. And in a parallel circuit, it's a bit trickier. It's the inverse of the total resistance is equal to the inverse of the sums. If I got that right. Let me make sure I got that right. I think I got that right. R to the n ad nauseum. Yes, okay, I got that right. Good, I'm not completely useless. Let's see, good real life application. You know those Christmas lights, holiday lights, fun stuff. You got a string of lights hooked up, and there's a reason they do it, and everyone knows. If one of these bulbs goes out, the whole strand stops working. And the reason's pretty simple, and we can explain it with Ohm's law. Each of those little lamps, each of those little tiny bulbs, because the wire is so thin, it offers a lot of resistance. But it's not very heavy, so it can't have a happy medium between being supplied with 100 volts domestic current, domestic voltage, and being thin and fragile. Otherwise, they just blow out all the time. So each little bulb in a strand of lights is like a tiny resistor that's only rated for 1.5 volts, maybe 5 volts. Let's use 5 volts. All right, so it's only rated for 5 volts. So obviously the logical solution to prevent having to tear your hair out and test a multitude of light bulbs to see which one is out. Instead, what they do is they wire them all in series. And each one's rated 5 volts, 5, 5, 5, 5, 5. They just wire them in series until there's enough to equal the 110 volts we're pumping in. 100 volts. We'll just use 100 volts. And so long as we have enough resistances in series, and we just add them all up, our light bulbs will be happy and they will not blow out. Any questions so far?
I'm going to pop off mute and just inform you that if you want to have questions, you need to pop into your question and answer app and ask if there's any questions or open it up for questioning, apparently.
Yeah, it's kind of.
It should be open. It's enabled. Sean managed to submit a question.
No, I typed in chat, I think.
Oh, there's a chat. I guess I should
Yeah, that's
check
the
that
chat,
too.
not the Q&A, because the Q&A has no entry form.
Yes, Greg, I'm sure you could explain the chemistry behind this much more better. So no one's Q&A app is working?
Mine's not, no.
I might have to
Okay,
drop
all
out
right. Well, if you
because my siblings are here and they're up to no good, so I
all
might
right,
have to.
it'll be
So if I
recorded so
leave, it's them. So
you can find it later.
I'll probably do that. I'm sorry. Like, good explanation. And honestly, I probably would have never figured this out through a textbook. Also, for that duration, I actually figured out how parallel that all that math later. Yeah, I'll probably come back when I can. So let's take care of
Okay.
people.
Yep, no problem.
So
Oh, why is it?
see you
What?
guys around, I guess.
Does anyone see a white banner at the bottom of the
Yeah,
screen?
I think that might be an advertisement. I
No,
think.
no, it's my screen.
I think it's only picking up that specific
There we
piece
go.
and it's just blotting everything else out, right?
There we go. It's fixed. I don't know what. That's weird. Whatever.
Well,
Um.
okay. Well, bye everyone. I have to go.
Okay, no problem. Bye bye. All right. So where were we? Let's talk about conductors again. So anything that isn't a conductor is an insulator. Copper is a very good conductor. It's actually the standard by which other conductors are measured, even though it's not the best conductor you could have. Uh, silver is a good conductor, but it's tad expensive. Gold is an excellent conductor, but again, not enough gold in the world to make every conductor out of it. There's a few generally metals. Metals are good. And if you want to get into the nitty gritty, if you go down on a molecular level, not a molecular level, an atomic level, and we have a look at our gold atom or whatever, and we've got a nucleus and an electron cloud, and we'll just draw a few levels here. Actually, no, we'll use helium. Helium's a good example. All right, and we've got our electrons orbiting our nucleus here. If we were to blow one of the electrons off, or blow all the electrons off, as in plasma, that's a good state of matter. Let's see. All right, so let's say this electron's missing. It's still a helium nucleus. We have a hole there. We have a hole for another electron to come along, a free electron, and go woo. There I am. And if there's another hydrogen atom next to it with its electrons blown off, oh, there's another one. And we can hop on through all our conductors. Oops, that was an awful circle. Atom, 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 so on and so forth. Kaboom. Yes. No, that would be if we split the nucleus. Hence the term nuclear. We're not messing with the nucleus. We're just talking about missing electrons and electrons going freely between conductors. Just so it's clear, helium's not a very good conductor. All right, so we have our good conductors here, pretty good conductors, and anything that isn't a conductor is an insulator. Makes sense. So what's a good insulator? Insulators. Wood's an insulator. Unless it's wet. Water is technically not a conductor. Actually, this is a good side note. Pure water, does not conduct electricity. It's when it's got impurities that do conduct in it. Things that are less conductive than water. Let's see, petrol, hydrocarbons. Those, especially kerosene and alcohol, those are very bad conductors, and they're so bad, in fact, that you can they can if you have them in a container which can generate a static charge just from the flow of the alcohol or kerosene or what have you, then you do have a kaboom. So that's why you have to use specific containers for kerosene and such. It has a static dissipative, basically a conductor built into the plastic, and that takes care of static charges. And my cursor has stopped working again. There you are. Right, so we got wood, PVC, plastics. Generally aren't very good conductors. Glass, that's a good one. Glass is an excellent insulator. Ceramics. If you go out and look on your power poles or pylons, things like that, you'll see these funny looking things that the wires are attached to on the pylons. They're kind of ribbed like this. That's a ceramic insulator. That's because even though the wooden pole it's attached to is usually a good insulator, it's not a very good insulator at those voltages. Wood also retains water, and water with impurities, and that'll be a good conductor, but ceramic is a very good insulator. So now that we've gone in this chemistry reprieve, let's go back to our our schematics. We talked about series circuits. Let's talk about parallel. So let's see. So whenever you combine resistances in parallel, we've got a load here, and we'll just do that. And we got another load in parallel. So if we have, let's say this is 100 ohms, and this is also 100 ohms. Combining those two resistances in parallel, we will always end up with resistance less than the two of them alone, because we've created a better path for the electrons to flow. So in this case, electrons will go through each resistor, assuming they are exactly the same value, equally. So we got the same current, same voltage across these 2 points. And if we took our little equation up there, which I think was, see, the inverse of the resistance is the sum of the inverse of each. Which should be 50 ohms. If I'm not mistaken. So we end up with a lesser resistance here. So if you think about it, think about ordinary domestic household sockets. If you've got too many if you plug in a lamp, let's say let's see, 60 watt. We can do the maths here. Note that this is not going to be 100% correct because we're dealing with alternating current, which we will get to a bit later. And the equations are slightly different because with alternating current, Yeah, well, let's go ahead and go into that right now. Alternating current is what's provided domestically, anyways, is always a sine wave. And instead of just having electrons always coming from one end and ending up at the other, it alternates. Aptly named. So you'll have a voltage rising on one side and then reversing on the other. And so this is our voltage time graph. So we've got voltage this way and time. All right, but let's go ahead and pretend that our equations are the same on AC. And let's say you have 100 ohm light bulb. All right. You could actually figure out, you could work the other way and go, let's say we have a 100-watt light bulb. Yeah, let's do that. This is watts. All right, and domestic voltage in Northern America is 120 volts. All right, and we know that P equals I squared R. And we've got 100 watts here. We need to find out the current. So I squared times our resistance. We need to find out our resistance. And we know that V equals IR. And we'll move you down here. I'm sorry. I wrote the entirely wrong equation. We know that power, that's what we're trying to get. Power is current times voltage. So we got 100 watts. Not sure the current, we know it's 120 volts. What kind of current do we have here? About 833 milliamps. Almost an amp. Boop. All right. So we know how much current we have going through here. Let's find resistance. So V equals IR. Got 120 volts through a load consuming 0.833 amps, our unknown resistance. So the resistance of that 100-watt light bulb is 144 ohms. There we go, 144 ohms. All right, so let's say we've got our light bulb here, and we've plugged it into our house. Boop, boop, and we've got happy electrons flowing up and down and through the light bulb, and yay! And now we're going to plug in another light bulb. And house wiring is, of course, in parallel. Otherwise, nothing would work if certain appliances were off. So we got another light bulb, another load, and we'll plug in another one. And we'll go there, that's the connection. And we've got our supply there. Now we got all these light bulbs in parallel. Well, we've doubled the current, Actually, we've tripled the current we're using. And the resistance has gone down. And eventually, we can add enough light bulbs in series that our resistance will be so low, on the order of a few ohms or 0.2 ohms. That's really low. Let's find out how much power you're using if you have a 0.2 ohm load. So P equals I squared R. And P equals V squared over R is actually what we want. So power is 120 volts over 0.2 ohms. Ooh, that's going to be big. 120 volts squared. Let's see. Plug it in. Wow. We're using 72 kilowatts. That's a lot. And we need our household socket to handle that load. And because the wiring, there's only so much wiring in your house, which is a certain gauge of a certain cross-sectional area. If we have that big of a load, we have our small resistances in our wiring, or the resistance from being a thin gauge wire. That wire is going to have to dissipate 7.2 or 72 kilowatts worth of electricity as heat before it gets to our load. And that is why, boys and girls, we have these magical devices called fuses and circuit breakers. A circuit breaker looks like this in a schematic. And we've got a fuse. And why'd you stop working? There you go. Fuse. Fuse is pretty simple. It's just a thin piece of wire that's designed to melt away before your wiring does. All right, where were we? We were talking about alternating current. We were talking about... we have a question. Sort of. P equals I squared R, P equals IV. IR units multiply into a voltage. Yes, Ohm's law. That goes back to Ohm's law. Because voltage is proportional to current. Let's talk about diodes, rectifiers. Let's change the color here. Alright, so we've got our... make a circuit. Actually, no, we're going to connect this to battery. Whatever. You'll be at point. Alright. Kind of funky circuit diagram, but oh well. One type of diode you're probably already familiar with is a light-emitting diode, an LED. We could go into how that works, the nitty-gritty, but all you need to know is that it is a diode. So we'll have a polarity. Remember, diodes are like one-way valves. They only let current flow from cathode to anode. So in this case, we can think of it as it only lets our electrons flow this way. It'll only conduct in one direction. We can also think of it as our current going this way, in the direction of the arrow. But let's say we were to if we put a positive voltage here, and a smaller voltage, or 0 volts, which is ground. That was an awful ground symbol. There we go. It wouldn't conduct. Electrons would go do, oh, and hit a wall, and wouldn't go anywhere. It would stop, this LED would stop conducting. Alright, let's have a look where we are. An older type of diode is a vacuum tube. Here's a good question to ask. Is a vacuum an insulator? Vacuum is normally a very good insulator. But because of something called the thermoelectric effect, if we have if we have a plate and another plate separated by a vacuum, normally nothing will happen. Absolutely nothing. We might get some few stray electrons. The only reason we'd get electrons moving is if we were to heat up one of these. So let's say we've got our heating element, and we make this plate hot. And we put some power in there. All of a sudden, our electrons have potential. And our electrons are going to go whee, here to here, here to here, through this plate. If we pipe in electrons here, they'll magically go to this plate. And conversely, if we put electrons here, they're going to go to this plate, and they're going to go, I have nowhere to go, because this has a lesser potential than this. And this is the basic operation of vacuum tube as a rectifier. It's got a heater element and an anode and a cathode. Whoops, that did not work. Q&A, no questions. All right. I wish it would make a noise when someone types in chat. Oh, we haven't even talked about voltage dividers yet. That's important. Let's talk about voltage dividers. So let's say we have two, yeah, that's crappy. Got a positive voltage supply, we've got resistor here, resistor here. Actually, let's simplify it. No, we're not going to simplify it. I'm going to talk about it here. Alright, so we've got R1, R2, we've got a positive voltage supply. And down here we've got 0 volts, which is our reference voltage. What would, if we had to measure the voltage here, I'm not sure what it would be, because it depends on these two values here. So we've got a positive voltage reference, and let me go back to my notes. Divider. There you are. All right. And there's a magical equation which I have neglected to memorize. You don't need to memorize this. But know that we get it from Ohm's law. Yeah, we'll go ahead and do the proof. So we know that our voltage here, we'll call that V in, we'll call that V out. So we know that V in is by way of Ohm's law and the sum of the resistances. Voltage is current times resistance, so it'd be the sum of R1 and R2. And we'll put that there. And we want to get V out. And we know that, let's see, it's going to be R2. It's going to determine the voltage here. Times R2. And we can take our triangle. Oh, I should have drawn the triangle first. This is a good way to know. You will want to memorize Ohm's law. It's pretty easy. And we can draw a little triangle here. This is an easy way to remember it. Boop, boop. So we know that voltage is current times resistance, or that current is voltage over resistance. Horrible R. And that resistance is voltage over current. Basic algebra. So we got I, and we can substitute our V over R here. V in over the sum of the resistances, R1 plus R2. And we plug that all in to our V out. Make sure I'm doing this right. Yes. The voltage in times R2 over the sum of our resistances. There we go. That's everything we wanted to find out. Voltage comes in here. What kind of voltage will we have here given these two resistances? It's a pretty simple game of ratios. And so we can use voltage dividers to get a number of different voltages out, which will be important. Let's move on to, well, let's see if we have any questions first. No questions. I guess no one's figured out how to use the Q&A app. That's fine. Let's talk about some alternating current. That was an awful line. I don't think we're going to get much better on this. We've all seen a sine wave, hopefully. It's a pretty awful sine wave. Sine wave nonetheless. And I'm being bombarded with messages. And this is just our voltage on the y-axis and time. Yeah, derp. I don't know why that was one stroke. Pretty simple sine wave we got going on there. And why do we use alternating current? You might have heard of the war on currents. This guy named Edison, who gets way more credit than he should, and this other guy called Tesla. And Edison didn't really have the mathematical background to understand alternating current the way Tesla did. This was a problem when we tried to invent the first telegraphs. We have miles and miles of wire, and of course, the longer a wire is, the more resistance you have, because we know that resistance is, come on cursor, resistance is a function of the length of a wire and its cross-sectional area, which I don't have a good symbol to represent it with. So the longer a wire is, the higher the resistance. Same with a smaller cross-sectional area. And Tesla figured out, hey, if you switch the directions that the electrons flow a few times a second, it won't solve the problem of great resistances, but we can put it into this thing called an inductor. And if you run current through a coil of wire, it'll set up a magnetic field. You can do this if you take a battery and a length of wire, wrap it around a nail or something metal, and plug in a battery on either side. Battery here. Horrible battery. Battery nonetheless. You'll set up a magnetic field. And hey, if you put another inductor close to it, another coil of wire. Why are you green? Come on, red. Then that magnetic field gets coupled and it creates a voltage. But the problem is, it would only do it for a burst, and then it would stop on DC. So hey, if you instead of a battery here, which only provides DC, I have no eraser, so we're just going to have to undo. Instead, you put an AC source and we couple those there. Then you end up with almost the same wave on the other side. The only thing that'll change is voltage, depending on the number of windings. So this is what we call a transformer. It'll take our, say, 100 volts, and we'll end up with the same amount of power on the other side, but we can change these ratios of windings to change the voltage. And Tesla said, hey, this is great, because with higher voltages, we know from Ohm's law, V equals IR. Hey, if you want to overcome great resistances, if you want to carry a lot of current over a big resistance, you need more voltage. So we can take our windings here. It's a pretty simple matter of ratios. So if you have 10 windings on this side to 100 windings on this side, and we'll draw more windings, then our 100 volts here gets multiplied by this ratio. We end up with, what, 1,000 volts. Oops, hold on. 1,000 volts AC. It's still the same waveform, but the amplitude's changed. We've got 10 times the amplitude. And this specifically is called a step-up transformer. And this is how power gets to your house nowadays. It gets generated at the station and stepped up to several thousand volts AC, and travels over much thinner wires than would be required if it was going to be 120 volts all the way. And then gets stepped down outside your house, probably at a substation, before it gets to your outlet. So another neat thing we can do, now that we're in the realm of alternating current, is we can have more than one phase. Let's say we have another voltage source that's perfectly 180 degrees out of phase with our first one. It'll look like this. Oops, and it'll look crappy. It'll be the same amplitude, roughly, as this one, but perfectly out of phase. Now, if you combine the two, you end up with nothing, 0 volts. But if you were to take the potential between them, if this is 110 volts positive, and this is minus 110 volts, if I can write today, the potential between here and here is 220. And that's how big appliances work. You've got 2 phases coming from the power company. You've got an X phase and a Y phase, and a neutral conductor, which we'll put in between. And if you were to measure voltage between the X and the neutral phase, you'd only see 110 volts. Same thing between the Y and the neutral phase. You'd end up with 110 volts, but between the X phase and the Y phase, because they are out of phase, you end up with the difference, the peak-to-peak voltage. Standing waves are a bit different. We actually do have to deal with standing waves in alternating current. If you think about wave physics in general, say you have transmission line, and it's terminated by resistance. All right, and we've got the same reference voltage over here. If you you send an AC signal down this line, if the source impedance isn't matched to this impedance over here, because it'll be like there's a resistor over here. It's imaginary. If this isn't matched well to this, you can have a standing wave ratio where some of the power, instead of being dissipated in this load, gets reflected back. Anyone else? No? Let's do this. This is boring. Let me switch my camera on. There it is. Here we are. Let me show you some components. If you can see them at all. I have no idea. This is a resistor. It's very blurry. There we go. This is a relatively small resistor. It's basically a piece of carbon painted with enamel. And you can see there's colored bands on it. Because resistors like this are much too small to read numbers off of, we used color bands to represent the values. And I think here we go. Pretty straightforward. Probably can't read that. But each color represents a number. So the first two going from the side without the gold band on it, which would be, in this case, left to right, I believe. Actually, it's inverted for you, for me, rather. So it's right to left. It'll be value, value, and then multiplier. We'll get to that eventually in construction. It's a resistor. Resistors are in all sorts of sizes. Here's a big one. This one actually got charred a bit. I pulled this out of something, forget what. Probably a power supply or something. This is a much bigger resistor. And it's not bigger because the resistance is a bigger value. It's bigger because this handles more power. This has more thermal capacity. It'll dissipate the heat much more easily than this little guy. This little guy would go up in flames if the resistance was low and the voltage was high. Get a lot of current going through there. We'll load it up. Talked about capacitors earlier. Here's a type of capacitor. This is an electrolytic capacitor. The way it works is you've got two pieces of foil, a foil connected to each piece, each lead here, and one is oxidized, and you've got an insulator between them, and it's all wrapped up and dipped in an electrolyte, a fluid of some type, probably a weak acid. And one side is oxidized. So you can charge this on a battery or a DC voltage source. I don't think that's going to reach. I'll do that in a bit. And it'll charge the capacitor just like a battery, and then you can reuse the current later. Let's see. Got a few different types of capacitors. These are ceramic capacitors. It's got a little number on them. I guess they figured they could fit numbers on disk capacitors, but not on resistors. Let's see. I've got some transistors here. Transistors are pretty important in modern computing. They're like an electronic switch. And we'll talk about that more in detail next class. There's all sorts of types of transistors in different packages. Some of these aren't even transistors. They're just integrated circuits in transistor packaging. Speaking of integrated circuits, here's some of these. I'm not sure what these are. I know what this is. This is static RAM at the bottom. This was probably in some sort of retro computer. An integrated circuit is a very tiny circuit, miniaturized down, etched into silicon, which is a semiconductor, which we will also cover in the next class. And I don't think I have much else. Oh, here we go. Here's some types of transformers. This is a toroidal transformer. So you've got basically a ring that's magnetic and two windings on either side. And I'm pretty sure this is a 1-to-1 winding. And, that'll be useful, even though it doesn't change the voltage. What it does is it separates the I cannot think today. Isolates the voltages and the voltage references. So if you want to get into construction, I don't know if anyone's interested in being able to build things after this. Any takers? You can go out and purchase a few things. I'd recommend a breadboard. This is a small, actually it's standard size breadboard. Basically, you've got rows of contacts that are all they're connected in by each row, each set of 5, and they're pretty good for prototyping. Oh, here's an LED. You've probably seen this, and we'll build a circuit for the next class and put it together and look at the schematic and trace the current through it, and then explain its workings. We don't really have very many diodes. Anyways, if you want to build things, decide to get into the hobby more, I'd recommend a breadboard. I would recommend some clip leads. These are nice wires with little clippies. Alligator clips, they're called. Most of this stuff can be had at Radio Shack, but it'll be a bit of a premium. For a bit more permanent things, we use soldering iron. This is a temperature-controlled soldering iron, which I would recommend if you do decide to get into any sort of construction. It may be tempting to get the cheap little, just the ones that plug into the wall. Those are good for a few things. But for good quality soldering, you're going to want a temperature-controlled iron. which isn't too expensive to come by anymore. Let's see. You want a breadboard? You want a few components for the next class. I'll post the component listing. We're going to be building a jewel thief, and we'll talk about boost converters, and that should be it. Let me see if I have anything else in here interesting. Oh, they're all in here. That's why. Here's some other types of transformers. This one's a big one. This one has multiple taps on it. Nothing interesting out here. No, don't go to sleep. Switch. That. Anyways, any questions? I haven't even been looking to fix things. And we're almost out of time. Questions? Go ahead, try me. Josh, would you rather speak the questions? Okay, go ahead. Why the opposites? Why do, in our circuit here, and we'll use red. Why are our electrons going this way and conventional current going the other way? And the answer is convention. It's just you know, they made a guess. They said, okay, this is positive and this goes this way, but the electrons are actually going this way. We also have to remember it's important that generally we like to think of the flow of current, the direction that current, conventional current, is flowing, because it might not always be a negative charge. Electrons have a negative charge, and in certain situations, you're not looking at the flow of electrons. You're looking at positive charges moving. Such is the case for certain battery chemistries. Battery is just two dissimilar metals in an electrolyte. Why won't I? Don't I have a? Let me pull something up. Why aren't you working? Yes, we have two dissimilar metals. So say zinc and copper, or carbon and carbon zinc is a popular battery chemistry. But we do think of the reference direction, because it could be the case that in an electrolyte, and Greg could probably explain this better than I could, you have not electrons moving from one plate to another, but you have cations, and which are positively charged, going from one state to another. A battery is always a chemical reaction. I don't know. How do you represent cations, Greg? No, it's not. It's not quite quantum theory yet. We're just dealing with battery chemistry. In lead-acid batteries, for example, it's lead plates, and because lead is normally not dissimilar, one is oxidized. That's probably wrong, isn't it? PbO, plumbum, lead. Lead's always a fun one. Lead oxide, and this will be the negative, and this will be the positive. This will be when it's fully charged. And as the battery discharges, the cations go into solution. The lead oxide plate gets converted to lead, and the other plate oxidizes, and you end up with free electrons. Does that explain it? Yes, yes, it is convention, but it also does have a reason, namely dealing with positive charges, and it depends on the environment. In basic electronics, with normal conductors like copper and such, yes, it's negative charges flowing, but it could be the case that we're dealing with positive charges as well, because as long as there is an electromotive force, so it could be in an engineering sense. We can look at a circuit, just arbitrary circuit. Let's draw something a little more complex. Inductor there, and the transistor, and that'll go back there. And so, like in a circuit like this, we might not know, depending on the state of this circuit, we have no idea which way electrons are flowing on which side. So we like to assign a reference direction and just say, okay, well, and this polarity is wrong. That way. And we'll just say, okay, let's say it's a charge going this way, because especially in this circuit, this is the circuit we're going to build Thursday. It's called a joule thief. It's a type of buck. Uh, it's a type of boost, voltage booster. So we'll think of it as this way. If you think of it as current, why did you stop working? There you go. If you think of it as current reference direction, when this circuit first gets turned on, when you first connect the battery, there'll be a positive voltage. We'll saturate this inductor, but an inductor allows DC current to pass, and it'll turn on this transistor. If you were thinking of it as flowing electrons, it might not be it wouldn't be immediately obvious that this transistor would turn on, because this is the emitter junction, and the way that transistors are controlled is by the base. Does that make sense? For this transistor to be on, yeah, and we'll explain transistors and rectifiers in more detail next week, or Thursday actually. We'll go into it. But thinking of it as electrons flowing backwards, sometimes it's just more obvious. Thinking of it as current forward, conventional current, just because of convention, and because of the way that the components got laid out. Same thing with diodes. Diodes only allow current in one direction, but we don't think of it. If you look at the schematic representation, it's easiest to think of it as current going this way, because it's the same direction of the arrow, rather than electrons flowing the opposite way. Okay, go ahead. That's a mixed bag of question. It depends on who you ask. With the way that power distribution is set up, where you have big power production facilities generating loads of power and then distributing them to houses that might be 30, 40, 50, hundreds of miles away, yes, it is, because AC we can change the voltage very easily with a transformer. Nowadays, it's there's a movement to high efficiency, high voltage DC distribution. It used to be the case 100 years ago that changing voltages from one to another was hard in DC. It was hard. We didn't understand switch mode regulation and buck boost converters, which we'll cover next class. And transformers are an easy way to do that with AC. Transformers do not work with DC, and the reason why is inherent to inductors. So if you have a coil, an inductor here of any value, we use the abbreviation L for inductors and inductance because of its name for Lorentz. I think that's it, Lorentz. So this is a coil wire. It's just a wire twisted in a certain way. So if we just put a direct, and get my cursor back here. If we just put a direct current through it, it'll just flow right through like nothing ever happened. But if we put an alternating current through it, it'll set up a magnetic field. And what happens is, so on the positive cycle in AC, all right, on and off, it'll set up at the peak here. It'll fully have a fully saturated magnetic field. Because of electromagnetism. This is probably the simplest thing you could build. Just wrap some wire around a nail or something, and apply some power to it, and you have an electromagnet. But on AC, what happens is you set up this magnetic field, and then when the voltage drops to 0, the magnetic field collapses. And when it collapses, it gets converted back into an electric field. And if it has nowhere to go, it'll end up back in the circuit. Where was I going with this? So the way a transformer works is it couples this magnetic field. Let me get my yellow back. We have a ferrous metal connecting these yellow, please. These two inductors. All right, so on this cycle, it'll set up a magnetic field. It's coupled to this. This magnetic field gets converted to an electric field. And now you have current flowing through this inductor. So a current induced on this one will also produce a current on this on the other inductor. Does that make sense? So on DC, you would just have the initial pulse. This is what DC looks like. You turn it on. It would set up a magnetic field, and it would saturate the core, and there would be initially on this inductor, you'd have, if you were to look at the waveform, it would look like this. It would be a spike, and then nothing. Rectified AC. Rectified AC would be DC. Right. So linear power supplies. You know those big ugly things you plug into your wall that are huge and never fit in power strips? That's a big transformer, basically. It's a few things. So we have I'll draw a schematic. You have your plugs. All right, and this is an AC source, so it's 100 volts AC, let's say, or 120 volts. That's a good one. And first thing it'll go to is a step-down transformer. So for a step-down transformer, we have, say, a 10-to-1 winding ratio. Okay. So we have 110 volts AC on this side. Across this side, we'll have 12 volts, or 120 volts down to 12 volts AC. And we'll feed that into a rectifier, which is our diodes, because diodes only allow current to flow in one direction. We'll set up our diodes here. Actually, we'll do this first. If we were to put a diode across here, and we looked at the waveform now, instead of our positive and negative cycle, the diode would end up with just the positive cycle, and the next positive cycle, and the next positive cycle. And we can put in another diode backwards. In fact, we need 4 diodes to completely turn that AC into DC again. That way. And then we need it this way and this way. There we go. And we'll have our negative supply, or 0 volts reference here, and we'll have our positive voltage here. So now our alternating current has been rectified by the diodes to only be positive, like that. And we can use our capacitors. We normally put some capacitance in there. So now we have our capacitor charging, and our capacitor would smooth it out. So we'd end up with something closer to this. Because this is the capacitor charging, and it'll hold the charge and start to discharge, and then the positive half cycle replenishes it, and you got this kind of a bit of a ripple. You can do this with DC, but for the technology at the time, it was impossible, and even now it's very expensive. All the parts in here are very easy to make and are cheap. This is pretty cookie cutter stuff. You can make a transformer easily, but to go from 120 volts DC, if this was just rectified over here, it would it would take a lot of componentry. Anything else? I think I'll go ahead and end the recording and switch everyone's audio back on.